So first of all, like what is a foundation model? So from Wiki, a foundation model is a type of machine learning model that is trained on broad data, such that it can be applied across a wide range of use cases. People have been calling, for example, GPT-4, segment anything, Dino, all of them foundation models. But I want to making sure like there's some kind of important caveats here, is that we probably have some very powerful foundation models for natural language processing tasks. But we currently still don't have an equally powerful like a vision foundation model. They can solve all the vision related tasks at the same level as how GPT can solve language related tasks. So even if we call, for example, segment anything or Dino, all of them like foundation models, but you have to recognize they are still only solving one specific type of vision tasks. Although, for example, some are like segmentations or some are learning this kind of pixel aligned like a visual descriptors. So although they are only solving those specific tasks, but they're actually solving those tasks at a very like a great performance, generalized very well, even like outside of what the model has been trained on. But those are some important caveats we have to understand about the difference between the states of the foundation model for natural language and the foundation model for vision. But for the sake of today's talk, I will call all of them foundation models and show you like some of the unique opportunities they can bring into our robotic systems. So specifically, I will talk about like 3 key opportunities we identify. The first one will be task specification. The second one is about this kind of low-level modeling of the environments, and then the high-level modeling of the environments. So start with task specification. The key questions we hope to answer is like, what is a task? And how to effectively communicate that task to the robots. So task specification in domains like self-driving cars or drones are relatively straightforward. You just tell the robots where the destination is. But task specification in the manipulation domain is not as straightforward. If you tell the robot to fold the clothes, what does that really mean? A clothes can be folded in many different ways. Or you tell the robot to set up the table. A table can also be set up in many different ways, depending on the user's preference. That means there's a lot of common sense implications behind this one very simple instruction, like set up the table. And there are actually a lot of like common sense knowledge learned inside those foundation models. So we want to making sure like we can harness the knowledge from those foundation models and be able to effectively communicate those knowledge to our robots. So we developed these systems called VoxPoser that doesn't really require any like robots demonstration data, and only using natural language instructions, they can allow the robots to do a wide range of real-world manipulation tasks with an open set of objects. So the inputs to our systems are simple, the visual observations and the language instructions. So using this language instruction to instruct the robots is not new. There has been a lot of work, especially recently from Google, where they have been training like a large-scale imitation learning agents that map from the language instructions, the visual observations directly into the actions. And I'm taking one example, RT2, and back then, like it's almost feel like Google solved the problem of embodied AI with a lot of press around it. But if you look at their results, this is actually the first demo on their website. I'm not doing any adversarial attack here. This is literally their first demo. The task is to move Volkswagen to Germany. You can see this model has some very high-level recognition capabilities, but the low-level execution, even for very simple pick and place, is not at a very satisfying level. The second example is to move Corvette to the US. Again, the high-level recognition is pretty good as it has adapted from those vision language models, but the low-level execution, even for simple pick and place, is not there yet. Obviously, recently there has been a lot of progress in further pushing the robotic foundation model forward, and this work like a Pi0. They also show some very nice performance. But if you look closer at their results, you also see some very weird behaviors. For example, like this. I'm not looping this video. It's just this robot I trying to keep trying again. And you could argue it really shows some great performance. Here's another examples where the robot just repeats itself again and again, without making any progress. So from my perspective, I'm a person, I believe in scaling. I would never bet against scaling, but the type of expectation, the type of performance we should expect from that scaling is still something we have to very carefully understand and very carefully calibrate in how we scale and what should we get after this type of scaling. So meaning like this direction is promising, but currently there's also a lot of hype about this kind of absolute performance and promise people get from this direction. So instead of taking this kind of end-to-end approach, we instead take a more modularized approach. So what we are like trying to get from this kind of foundation model is this kind of some kind of plannable intermediate representations as expressed using code. So why using code? Code is great because it is simultaneously large language model generatable, human interpretable, and robot executable. So this acts as some very nice multilingual intermediate interface to bridge between the foundation model and the robot interactions. So there's two core insights for this work. One, we use foundation model to specify the task. And second, we use code as this intermediate interface to bridge the gap between those models and the robot actions. Here's how the system works more specifically. Again, given the visual observations and the language instruction, open the top drawer. The large language model will generate codes that specify this 100 by 100 by 100 like voxel grids. It will then call an open vocabulary object detector to detect where all the handles are inside this environment. In this case, there are 2 handles, and the task is to open the top drawer. So the large language model will generate additional codes to rank the handles according to their height and only leaving us with the top drawer. And then we can assign some values associated with the 3D location of that top drawer that can give us some kind of affordance map. And at the same time, you could also say, watch out for the vase along the way. The large language model can generate additional codes to detect where the vase is inside this environment, and then assign like some negative values to the location associated with that vase to return this smoothed out 3D constraint map. So we have affordance map, we have constraint map. We also have a series of other maps like rotation maps, repair maps, and velocity maps to specify the pose of the end effectors. All of those maps composed together, we call it this value map for the robot to do motion planning. If you are familiar with like robotics terms, you can also call it like a potential field. And we essentially doing motion planning within this kind of 3D voxel-based objective functions to plan the robot's behavior that is able to accomplish this task, like open the top drawer and watch out for the vase along the way. And this framework can also be applied to a wide range of like other manipulation tasks. For example, here we are showing some very basic articulated object manipulation tasks, like close the top drawer, turn on the lamp, or turn open the vitamin bottle. The robot can recognize which bottle is the vitamin bottle and go there to open the cap. You can also do some basic deformable object manipulation tasks, like take out the napkin, sweep the trash into the dustpan, and also hang the towel on the rack. Where the large language model is decomposed. Yeah, please, question.
When you have the sense detective vase, so you put some clearance map around it. But it's not just the manipulator, but when you open the drawer could bump into the vase as well. So how do you, foresee this possible?
Yes, that's a very good question. So meaning like there's actually a lot of constraints you probably have to think through, especially the relationship between different kind of objects. For this specific work, what we're trying to do is essentially trying to transform this kind of language instruction into some kind of objective function for the robot to do planning. We want to show that this is possible and applicable into a wide range of tasks. And this is actually one limitation of this work that doesn't really consider some very fine-grained like constraints between objects. And I'm going to talk about the next work that will be able to handle this.
This is one shot. You do the planning, you figure out geometric constraints, you do your manipulation.
Actually, it is one shot. The code generation is just one shot, but the code can contain some kind of while loop I will show later that allows it to be robust to external disturbance. And here are just some like a basic deformable object manipulation tasks and many other like everyday manipulation tasks, like take out the bread from the toaster, lay it flat on the board, set the table for the pasta, and also measure the weight of an apple. The robot can recognize it has to use a scale to measure the weight of an apple and be able to place the apple on top of that scale. Like I mentioned, like although the generated code is fixed, the code can contain some kind of logic to allow the robot to be robust to external disturbance. Like from the left example, it is to sort the paper trash into the blue tray. And after the robot is trying to do the task, there's a person constantly perturbing the robot from doing its job. And the robot will be able to constantly detecting where the trash is, where the blue tray is, and be able to manipulate that trash into the blue tray. The right example is to close the top drawer. After the robot closes the top drawer and the humans come in again, like mess up with the environment, the robot knows to know the drawer is still open and be able to go there and close the top drawer. And during the investigation, we also find there's some kind of very interesting common sense behavior level reasonings. We can just give the robot some follow-up instructions. You tell the robot, I'm left-handed. The robot can generate additional codes and to generate these objective functions that allow the robot to move the fork from the right side to the left side. And or you can tell the robot you are off by 1 centimeter to the left. The robot knows to generate additional code to synthesize actions to move the leads 1 centimeter to the right in order to close.
You were saying something about the seminar?
They're gonna do like a Rob seminar.
Oh, the one you were here for.
Yeah. I'm thinking of like some.
Oh, no. With a host.
Christina is the host.
Okay, so I guess I'll just continue. And the third example is actually quite interesting. The task was open the drawer precisely by half. Now think about how you actually will do the task. The robot come up with a strategy that first open the drawer fully and push it back for half the distance in order to do the task, open the drawer precisely by half. So to summarize a little bit about this work, the key insight is that we use foundation model to specify the task, to communicate the task to the robots. And we use code as these intermediate representations that bridge the gap between the foundation model and the robot actions. It allows few short generalizations, meaning we have to give some kind of in-context example to the robots, and the robot will be able to generalize to a wide range of tasks than what's specified in those in-context examples. Any questions?
How does the robot detect the change of the environment?
So what happening is actually this. So I'm showing the prompt here. From here is actually I'm can see my cursor. We have this object list, for example, trash can and the napkin. We also have the query, which sorts a napkin into the trash can. Those are the 2 lines of code we input to the large language model. All the remaining code are generated by those large language model. It can actually generate code that contains the while loop. The while loop essentially detects the distance between the napkin and also the trash. As long as they are further away, from certain distance thresholds, it will constantly detecting where the trash is, where the trash can is, and redo the task. So that allows the robot to be robust to the external disturbance.
This is generated top-down without looking at the visual.
This is generated from top-down. This is because this work was done in 2023. Back then, we only have GPT-4. We don't have GPT-4 V. Back then, the foundation model is only able to handle language instructions. So we just live with that. So the code is fixed after the robots see the language instructions. But we're gonna deal with that in some later works.
So usually the LLMs are not trained with mobile data. So for example, we don't know the kinematics of robot and shape of robot. Will that need to some limitation of this method?
These are very good questions. So again, you can see this work is actually a lot of evaluation that's still on a very empirical level. We did a lot of evaluations and we're trying to be a bit more rigorous in providing the error breakdown. What we realized was the most errors were actually coming from the perception model instead of from the generated codes. The GPT-4 back then was actually pretty reliable in generating executable and good code. Obviously, it still contains some errors, but the majority of the failure cases actually coming from this kind of open vocabulary object detector. So I guess I will continue. So regarding the limitation of this work, like we just mentioned, it's actually limited in terms of the spatial resolutions. It only contains where the robot should go and where the robot should avoid. It doesn't really consider the fine-grained interactions or fine-grained relationship between different types of objects. It is also limited in terms of the temporal constraints. It only consider the dynamics of the robots, doesn't really consider the dynamics of the environment. And we also assume that all objects are observable and also lacks feedback to the foundation models. So we want to improve upon this. So that leads to the second opportunity we identify, which is trying to build better low-level modelings through the use of foundation models, especially through this spatial temporal relationship constraints. Take this a seemingly simple task as an example. I pour the tea into the cup. If you really look into what's happening at different stages of the task, you realize at the end of the first stage, the robot gripper has to get in closer to the handle parts of this teacup. And then at the end of the second stage, you want to making sure the tip of this teapot is right above the cup. And during the process, you don't want to like wiggling those teacup around. And at the end of the third stage, you want to making sure like the teapot is being tilted into certain angles. But during the process, you want to making sure the tip of the teapot is always right above the cup. That essentially specify the axis at which the robot rotates. So meaning there's a lot of nuances, like the relationship between like different entities that actually needs to be considered through the planning for this specific task. So for this purpose, we use foundation models for this kind of low-level scene modeling, like through spatial temporal like relational constraints. So on the high level, like what we do is to decompose the task into like a several stage. And for example, here we show 4 stages, like recap 1, recap 2, recap 3, and recap 4. And within each stage, we have a number of key points that describe different semantically meaningful parts of this environment. And we describe their relationship, their supposed relationship within that stage. And given this kind of spatial temporal key point constraints, we will be able to use optimization to solve the robot's actions. Here's how it actually works, like more specifically. Like given this environment, we have the teapot and the cup. We use the combinations of segment anything and the dino V2s to assign key points overlays with original like a visual environments. Essentially, what we do is to do clustering over the dino features that will allow us to have key points on semantically meaningful parts of this environment. And then given these visual observations and the key point overlay, like together with the language instructions, we'll feed them through this vision language model. It will first decompose the task into several stages. It will then generate 2 types of constraints, both the sub-goal constraints and the path constraints. Sub-goal constraints essentially describe how the key points should be relations with each other at the end of their task stage. And the path constraint specifies how those key points should be constraints during the executions of that stage. Like I mentioned earlier, given this kind of like a pouring tea from the teacup as an example, at the end of the first stage, the end effector should be getting closer to the handle parts of this teapot. And then the second stage, the tip of the teapot should be right above the cup. And you don't want the teapot to wiggling around. So you want to making sure the key points of the tip and the key point over the handle, they are always at the same height. End of the third stage, you tilt the teapot over a certain angle. And during the process, you want to making sure the tip of the teapot is always right above the cup. So meaning at different stage, you are generating this kind of spatial temporal constraints. And at different stage, they are also focusing on different subsets of semantically meaningful parts of this environment. And then you can do constraint optimization to optimize the robot's actions. This is essentially just sequentially square programming to optimize the robot's actions. And one interesting thing about this framework is that whenever the constraint has been violated somewhere during this process, you can actually like trace back to some earlier parts of this whole like a task level plan until a point where all the constraints are being satisfied. And we do the optimization from there to be robust to like whatever unexpected events happening inside this environment. So we evaluate these systems on 2 real-world platforms. The first one is like a mobile robot, not really mobile, it's just like a cars with an arm where we move them around. On the right, we show this kind of bimanual manipulation setups. And here we show our results. The left one is the actual execution. The right one, we show the real-time like plan trajectories overlaid with the original like a point clouds. Here's another task. You can see like we want to store the book into the bookshelf. The robot has to reorient the book over a certain angle before you can do this kind of insertion. On the right, you can also see like the trajectories has been like changing as the robot finishing the current stage of the task. Here's another example where we want to like insert the Cocoa can into the recycling bin. You have to rotate the Cocoa can over a certain angle before you can actually like throw this Cocoa can into that hole. And here's another example where this kind of bimanual robot is trying to fold the clothes by like specifying the key points on different like areas of this clothes and trying to specify the relationship between them, both like within the both at the temporal level and also at the different like a task stage level. Here's another example where we're showing the robot can do some kind of like collaborative foldings, where it is constantly tracking where the human hands are and be able to move the end effector, the corner of the clothes, closer to the human hands. So in this work, we have been very careful in understanding like the system level design and system level efficiency. So our key points can be tracked at 30 frames per second, and the optimization can be done at 10 frames per second. It allows us to do closed loop replanning, both within the task stage and of course, different task stage. Here's the examples of pouring the tea under the disturbance. You can see as a human messing up with the robots, the robot can like constantly detecting, like tracking the movements of the teapots and also the cup and be able to accomplish this task. And here is actually the interesting part. Here, the robot already like finished the task. The humans mess up with the robots. The robot knows to like trace back to some earlier stages and reduce the optimization from there to be robust to this type of like a disturbance. We also show that our framework can generalize to clothes of different configurations. Like we try like different like shape of clothes, and the robots can always generate some kind of reasonable strategy to understand like how different shapes of clothes should be folded. Here's just another set of examples. So to summarize a little bit, for this work, the key insights to use vision foundation models for like a lower level, like a scene modeling. And task modeling is modeled as this kind of spatial temporal key point constraints, and with constraint optimization for motion planning. And take home message for this work is that the VLM generated codes remain to be extremely versatile in specifying a wide range of the tasks for the robots to do. And the key points actually provide some very fine-grained like modeling, both for the scene and both for task, that allows us to know, like for example, the key point on this object has to always maintain certain distance from a key point from another object. It allows us to avoid the collision between the objects within this kind of environment, to answer your question. And it also has some very nice connection with the whole fields of task and motion planning. And we allow closed loop control both within and of course, different task stages. It is really a way to leveraging different modules for their strengths, where the vision language model is used for task interpretations and the constraint optimizations is used for this lower level motion plannings. Meaning we are not doing things end to end, but we really understand the advantages and limitations of different tools and be able to like have this kind of integrated systems to allow us to get the best of multiple worlds. Any questions about this work?
It seems to me that the selection of these key points is like critical to this process, like being performed well or correctly, or its convenience or easiness. So how is it that, or does it always get the proper key points? Like you can imagine it chooses a different set of key points that aren't as conducive to the task, but would still be sensible for the object. Like how does the key points part work? And if that makes a mistake or orients it in a different way, how does it recover?
That is a very good question. So for this specific case, like what we are taking advantages of is this kind of like earlier work I showed here. It's called Dino, shown on the right. So essentially you can see the visualizations of the pixel aligned features that actually give you some very interesting and good semantic level descriptions about different parts of an object. So what we did was to like fuse this kind of information from multiple cameras into this kind of 3D unified space. And we do clustering over this kind of like a visualized like 3D space. And if we do clustering, we actually can have key points over semantically meaningful parts of these environments. And we obviously have the assumption is that like assuming some levels of densities of the sampled key points, like you actually covers all the task relevant regions for that specific task. And during each stage, the foundation model doesn't have to be using all key points at the same time. You only have to select a subsample of those key points and specify the constraints between them. So that is how we are like making sure like we have like a key point set that covers task relevant regions of this environment.
Okay, and it sounds like it doesn't generate key points that are irrelevant to you. Like that doesn't seem to be a problem that you solve, or like does that ever happen where it generates key points that cause it to fail, where the task is not possible?
There is like for example, in this case, you can also notice like many of the tasks is still like can be done by, for example, pick and place and pick and move, pick and pull, those type of motions. And obviously, if you want to do like more dynamic tasks where you have tasks that needs to have like a better understanding about the dynamics of the environments. And then like, for example, the set of key points and the dynamics between those key points becomes like even more matters. So currently we definitely like see scenarios where we don't have sufficient coverage about task relevant regions of the environments. And also in tasks require like a higher levels of dexterity and maybe more dynamic tasks, it can also fail.
Robots see what we see, or robots see what the manipulator sees.
So robots have some externally mounted camera looking at the environments, and that camera sees the input from that camera will be fed into the robots.
So what about a vase, cylindrical, completely symmetrical, where what will your key points be?
In that case, because like you can see like the left wing is actually like have similar color on the right wing. So actually in this kind of like symmetrical objects, if you visualize this kind of dynamic feature, you also have capture this kind of symmetries, meaning the features will be different at different heights of that vase. But along, so then the peripheral of that vase, it will actually give you like a very similar like features. So meaning in this case, where if we do the clustering on that vase, you will have key points for them at different heights of that vase.
Medial axis.
Yeah, medial axis.
How are you going to grasp based on that?
So at the lower level, because we understand, like for example, the ND factor has to getting closer to some key points, or we can certain relationship between different key points. And if we need to grasp, we actually call like another like a supposedly a very good like a grasp planner called AnyGrasp. We'll use AnyGrasp to like synthesize like local grasp, meaning like when the robot knows it's getting closer to some key points and you have to like perform these grasp actions, then we call AnyGrasp to like synthesize local grasping actions.
So coarse guidance from your.
Yeah, coarse guidance from this like key points. So then I will continue. So this is about like the take-home messages for this work. And then we are going like a one level higher to understand how those kind of like a foundation model can give us like a higher level and then larger scale like a modeling of these environments. Specifically, when you understand like how it can enable us to have a better understanding about the scene structures, to like do better explorations and have memories about this environment. So talking about the scene structure, like scene graph has been like one of the like works that's like I know many of you like Bernadette has this very like nice work VLFM. So scene graph is actually very good in capturing like a larger scaling and modeling the larger scale environments. But if you look at all of the existing, like nearly all of the existing like scene graph work, you realize they have like one very important missing piece, which is action. Meaning the robots are doing active perception, but it is not doing active interactions with these environments. And if you want to have a robot that is useful in your home environments, for example, in the kitchen environment, the robot has to understand where all the ingredients are and where all the utensils are by opening the drawers and doors in order to find those objects and memorize their locations for the robot to be useful in your home environments. And on the bottom right, I'm having a video from like a Tom and Jerry. Obviously, they are looking for something. But during this kind of like exploration process, they are not doing like a random motion, like waving their arms like randomly in the air. They identify what objects require explorations and also understand, given that object, what should be the right actions to interact with that object. And they also memorize the details of what they have explored for the downstream tasks. So then we build this framework, which allows the robot to explore the environment through interactions and also memorize what it has seen. For example, here, like we are showing like a tabletop environments where the robots have to understand what's inside this fridge and what is inside those kind of like drawers for the robot to have a full understanding of the environment. The robot will first like scan the environments, like then like be able to identify like, this kind of scene graph shown on the top left, and it will also then ask like what nodes can be further expanded, and then identify the right action in expanding from that node. So for example, the drawer can be opened, and after you open the drawers, you identify the condiments, the forks, the cans from all those like hidden areas. And then given this type of scene graph, the robot can use this scene graph to do downstream task. To do the downstream task, the robot has to retrieve all the objects from the right location. And the retrieval of those objects is as simple as just go through this scene graph, execute all the actions along that path. Your robots will be able to see that objects. Here, the robots will like open the drawer of the refrigerator and place the Coke can on the desired location. Until here, the task is actually not accomplished. The robot still needs to like place a spoon on the left side of the plate to finish the task. But the robot knows from its memory that there's no spoon inside this environment. The robot will ask human for help and to place a spoon on the left side of this plate. So this is a nice thing about be able to properly do the explorations of this environment. And here just like an overview of how the system works. Like given this environment, we will have like combinations of like foundation models, vision foundation models to do the perception task, and we will be able to generate this kind of memory. This memory contains this kind of action conditions, like a high-level scene graph description of the environment, and also this kind of low-level, like a description about the geometry and semantics of this environment. And those will be fed into the foundation model to ask, basically, what node can be further expanded? If you want to expand that node, what should be the right action to expand that node? And then we'll execute that actions to close the perception, memory, and action loop. Here's just like one memory we built. The top right is essentially the environment the robots wanted to explore. And here, like we can have like different like objects and highlighted. You can also see the tape that's hidden within this like cabinet, where the robots can able to understand the relationship between the hidden objects and also the overall environment. Here's another interesting example where we are given the foundation model feedback for the robot to like do further explorations. So this is a nested dough. After the robots like pick up the first layer, there's like a more like a doughs appearing. The robot will be able to keep on doing the exploration until it sees nothing. They'll be able to build this kind of stack like a scene graph and be able to use that scene graph to recover the environments into the original state. And in collaborations with researchers at the Boston Dynamics AI Institute, we are also expanding them into the larger scale environments where the robots like this spot robots with the arm are trying to like explore some kind of larger scale environments. You're able to identify this cabinet needs explorations. You'll go there, open all the doors, and be able to like see what's inside those cabinets and be able to update its understanding about this environment, both at a high level, the scene graph level, and also this kind of low level, this kind of semantic level. And the robots will also identify this box can be moved around, and the robots will move the box away to review the hidden objects behind that box. And after the exploration, you could ask the robots to do tasks like collect all the toys. The robot will retrieve from its memories and be able to like put all the toys from their original location and place them into the basket inside on its back. And it will go like to find all the toys and place them on the basket on its back. Here's just some like other experiments where the robots identify that the chairs can be moved around, and the robot will go there, move the chairs away, and then like to review the cabinets like behind it, and then go there to open the cabinets and be able to update like its understanding about the environments by seeing like what's inside that cabinet. Here's another example where the robot is able to identify this desk and trying to review what's beneath that desk by sitting down. And they can like also update the scene graph by having this kind of node describing the objects that are underneath this desk. Here's another example where the robots like identify there's some kind of clothes. They'll go there trying to lift up the clothes. And similar to the nested dough example, there's another clothes. The robot knows to like lift up the clothes again and be able to see, for example, the bottle underneath that clothes. This really shows that this type of framework has the potential of generalizing and extending to larger scale environments. So to summarize a little bit, the structure about this work we are using is called action conditions, like a 3D scene graph. It's essentially using the foundation model to help the robots identify what object to explore, understanding how to explore those objects, and memorize what they have seen. It can also thinking it from the other way around, which essentially is trying to augment the existing foundation model with some kind of physical embodiment that allows it to interact with the environment. That's essentially like also provides the foundation model with this high level and low level memory. And this memory will allow the foundation model to not be limited by its like context length and support a wide range of downstream like manipulation tasks based on like retrieval from its memory. So any questions?
So if I remember correctly, for RoboX, like I remember the scene was sort of recovered to its original state to sort of like keep the scene structure the same. Whereas I'm just realizing that for Curious Spot, that's not the case, right? Are there ways to like put the robot's own action into how the scene graph evolves over time?
Okay, that is actually a very good question. So in Curious Bots, we didn't really recover the environment, we just explore the environment and already update its memory about the environment and starting to do the tasks. So then there's always a question about do you need the recovery or not? And if you were to do the recovery, do you want to making sure all your actions are reversible or not? Some action might be reversible, some action may not be reversible, and sometimes you want to prioritize those reversible actions compared to irreversible actions. So those turn out to be a lot more complicated than we initially expected. So in this case, we didn't really go into that, but that's definitely worth some further investigations.
In the kind of first section of your talk, we were looking at these voxels, and it was a robot was kind of navigating through that space. I'm wondering what governs the size of those voxels, and that has to be related, I think, both to the robot's morphology and also the task, or maybe compute. So I was kind of wondering what governs the size of those 3D shapes.
That's a very good question. That has also been a question I've been thinking a lot about. Essentially, what you're asking is that at what levels of abstractions should you represent this environment? And for many of the things we have been doing, we just fix the levels of abstractions. It either, I mentioned earlier, 100 by 100 by 100 voxel grids.
Okay.
I will assume it can solve the task we care about, at least in that work. And in this work, we're having this kind of 2 levels of abstraction. This kind of scene graph, which is at the symbolic representation level, and also the low level geometry and semantics. So they also can be very nicely interact with each other. For example, the action is decided using what action primitive to use. It decided through this kind of symbolic structure, and the specific parameters inside the action primitive, which direction should you go to approach that handles, is decided by this kind of low-level geometries. They can also be very nicely work together. But in order to really answer the question how to adaptively select the levels of abstraction has been a very fascinating question. Meaning, for different tasks, the levels of abstractions might need to be different.
Yeah.
Grabbing the water bottle compared with opening the cap of that water bottle, the levels of abstractions can be different. Also, depending on the object, interacting with a rigid object, the levels of abstraction might be different from manipulating a pile of granular pieces. And even within a task, if you want to grasp an object that are far away from you, you only have to know there's an object. As you're getting closer and closer, you start to realize you have to know the detailed geometry in order to plan your grasp. Meaning, depending on the task, depending on the object, depending on even different stage of the same task, the levels of abstraction may need to be different. And that I have been thinking a lot on, and I don't think I have a very, very principled solutions to that. So currently we're trying to understand the pros and cons of different levels of abstractions, and then gradually going towards that direction.
Got it. So that sounds like it's an open question.
It's an open question.
Got it. Thanks.
Yeah. So then I will continue. So those are the opportunities I told you about the progress of foundation model can bring to the robotics, meaning task specification, low-level modeling, and high-level modeling. But working with those foundation model seemingly to be good in some of those examples, but was not fun. They involve a lot of empirical interactions with those foundation models. We get to see a lot of failure cases. And especially it is very limited in terms of its understanding about the geometrical, physical, and embodied interactions. Here are just some simple examples. I gave these figures and asked GPT-4 which one is longer, A or B. It says both arrows appears to be of the same length. It might confuse it with some kind of very famous visual illusions. And one interesting thing is that it asked me a follow-up question. Do you want me to generate some code to analyze this image? I'm not sure, do it. You generate some code, call some OpenCV libraries, and they do the execution and solution. The conclusion was, yeah, they're of the same length. So it really is kind of limited, also being somehow biased by what type of data they've been trained on. And obviously, Sora has been quite amazing. It was actually first announced 1 or 2 years ago. People see those amazing videos. But recently, as people can start to interact with those a Sora video generation, you realize from a computer vision perspective view, this video actually pretty impressive. But if you read the physics and the structure and the geometry within those videos, you'll realize a lot of failure cases on satisfactoring generations from it. We're also trying to understand does it understand the effects of an actions. Here we ask the GPT-4 to say which directions should you pull in order to open this this fridge. It says yellow. Yeah, it looks reasonable. And we change to a different camera viewpoint. Now it says green. We change to another viewpoint. It says yellow again. You want to pull from the yellow direction in order to open the fridge. On the back, we actually have chain of thoughts. Meaning we are not doing the most naive way. We are trying to make them work better because we want it to work better for us to do robot interactions. So meaning we identify the foundation model has bias over different colors, has bias over different kind of labelings. So that's why in the recap we converge using 1, 2, 3, 4 those kind of overlays. But the way you are interfacing with those foundation model, that actually requires a lot of empirical understandings to really converge into some a more suitable interface. This is mainly because it does really have a good way of understanding the effects of its actions. So in order to make the current foundation model better and really go towards this foundational robotic models, I identify 3 major missing pieces. And our lab has been very actively working on in bridging and in providing those 3 missing pieces. The first one is about sensing. It's specifically tactile sensing. Tactile sensing plays a hugely important role for us to understanding our detailed interactions with the environment. For example, in this example, if you just from the vision, it's very hard to know whether it is a loose grasp or a tight grasp. And you are sitting there, why do you know you are sitting in a stable posture? It's a tactile sensing from your body tells you you are sitting in a stable postures. So actually touch plays a very important role for us to make these fine-grained interactions, even in cases pull the keys from the pockets, button the shirt without even having to looking at the interaction process. And during my PhD at MIT, we built this kind of tactile glove, which was published in Nature, where we have dense tactile signals on the thumb areas. You can see on the left is the interaction, on the right is the response from our tactile glove. It tells you where you have contact, how much force you are getting. And as you are trying to press on the rim of this a mug, you can see this kind of circular contacting patterns, tells you those local contacting patterns. And this glove is actually collected by the MIT Museum. So whenever you have a chance, this will be the first thing you see when you enter the AI section. So we improved upon the sensor as I'm starting to become a professor, to making sure this sensor is compatible with robots. And here we are showing our improved versions of that sensors, although in a square shape, to be able to sense a different type of interactions between the objects and also the sensor. And we equipped this sensor on the robots and allows us to do some very fine-grained and complicated manipulation tasks. The top right we are showing examples that's in doing grasping of the grapes under heavy visual occlusions. On the top right we are showing we can handle fragile objects. Bottom left we show some very precise in-hand manipulation as well as bimanual coordinations that involve some kind of sliding between objects and sliding between the objects and the fingers. And as we released the sensor, we received a lot of enthusiasm, both within academia and the industry, both within the US and outside of the US. We started to receive many videos. Just within a month, we probably received 15 videos where people trying to reproduce our sensor because we released very detailed fabrication guides. And looking at those videos, you can totally tell some people's reproductions was better than some other people's reproductions, depending on their backgrounds. But we are very happy and we love to doubling down and pushing this direction further to democratize the tactile sensors we built. This is about sensing. The second very important pillar, I would argue, is about the understanding about the dynamics of the environment, essentially understanding the effect of an actions. So we humans have this intuitive model in our minds. We can predict how the environment is going to change if we apply our specific actions. This has been a capability that the foundation model, the current foundation model is actually very bad at. So looking at these videos, we can predict how the dough will change its shape and how the onion pieces will move around. It's exactly this kind of predictive ability that allows us to plan our behavior in achieving those targets states. Our lab, actually starting from the first year of my PhD, and I'm trying to be learning this kind of word models of these environments, especially using a particle as a representation and graph neural networks, which allows us to do manipulations involving deformable objects like fluids, clothes, robes, multi-object interactions, and also this best system papers awards, which allows us to choose from 15 different 3D printed tools to manipulate a dough into a dumpling. And our lab has also been pushing further in these directions. And this is actually very recent results we get, where we are getting this kind of action condition like a 3D video predictions. You can call it like a 3D word models. So we just allow the robots to randomly interact with the rope for 5-10 minutes. Based on this data, we'll be able to build this neural digital twin. By neural digital twin, we mean are the reconstructions of the appearance and the geometry shown on the left, which Gaussian splatting, nothing new there. On the right, we are showing our pure neural-based simulators. On the top right is actually the robot's teleoperation through keyboards. This is actually a teleoperated neural simulators, and all the robots and ropes are simulated by neural networks. We can just teleoperate the movement of the knee factors. We can predict how the arm will move around and how the rope will deform as you input the different actions. On the right is actually a screenshot, so this is actually running at a real time. And this can also generalize to a diversified set of objects like clothes, ropes, stuffed animal, as well as some boxes. So this looks like dynamic Gaussian, but this is not dynamic Gaussian. This is action condition like a 3D video prediction. And very recently, we are also trying to navigate along the spectrum about how much structure we want to add to this kind of dynamics model. Here's our very recent results. On the left is actually the observations of human interacting with some deformable objects. In the middle is actually our reconstructed object states over time, which is tracked over time, as well as the human actions. On the right, we are showing this kind of interactable digital twins we reconstructed from just a few seconds of a human interacting with those deformable objects. And this an interactive digital twin, we have the appearance, have the geometry, have the dynamics, and we render that and overlay that with the original video. You can see our overlay with the original objects very, very nicely aligned with each other. And obviously, if you have a digital twin, you can start to regard it as some kind of game engine to start to interact with it in a random fashions. Here, we could have rendered the shadow, which will make it look more realistic. But you can see we can reasonably capture the geometry, appearance, and also the dynamics. It can also be applied to many other objects like a stuffed animal, clothes, ropes. And on the bottom right video, I think the students recorded the example trying to fold the clothes through this kind of teleoperations. And this is the example where we show how it can be applied to robots. And here on the top left, we have this gallows set up by manual teleoperations. We are teleoperating the robots to move the clothes around. And on the right, we're showing this kind of real-time overlay between what's actually happening in the environment and the digital twins that is being controlled in an open loop fashion through the actions recorded from this gallows. You can see our open loop prediction using our reconstructed digital twins has some very, very nice alignments with the original videos showing its effectiveness. And this is obviously real time. Our implementation is on using NVIDIA Warp, can be run in a very efficient manner. And then the third pillar, arguably speaking, and you won't be surprised, obviously, is about the data in order to scale things up. Our labs have been involved in this OpenX, which collects a large amount of robot data across a range of robotic institutions to aggregate this kind of real data. And in collaboration with Stanford, we are also continuing the developments of this kind of behavior benchmark that's trying to doing scalable generations of simulated data. We have also been collecting a multimodal data, including tactile data, gaze information, audio information, human body pose information, and even muscle signals. And to capture the interactions between the human and the environment, especially in the cooking domains, a lot of kitchen scenarios are being considered inside this data set to understand how different modalities are overlapping and complementing each other. So those are three, what I argue, most important pillars to really getting us towards this foundational robotic models. And finally, I want to provide some of my definitions about this so-called foundational robotic models. I want to draw some inspirations from this foundational vision and language models, meaning their outputs may not always be perfect, but it will always generate something that look reasonable. And what I hope to achieve with this kind of foundational robotic model is that the synthesized action may not always be optimal, but the generated trajectory will always be beautiful and reasonable. That I believe has always been something people hope to achieve with this kind of large behavior models or like this kind of foundational robotic models. And given the language instructions and the visual observations, the robot will just do something that is reasonable given that specific scenarios and allow the robot to do a wide range of tasks around us. I'd like to thank all my collaborators. Without them, it would be impossible to do all the works I have shown before. And I'm happy to take any more questions. Thank you.